Hello, welcome to Team 4's Interim presentation. Our project consists of analyzing and redesigning a personal humidifier. A personal humidifier is USB powered and contains ultrasonic transducers to convert water into tiny droplets. The droplets are then dispersed using a fan. The mist is blown through an outlet to be released into the surrounding area. The exterior of the device consists of a metal casing with a plastic cap on top. Within the casing, there's an electronic panel that houses all the electronics. Based on our market research, the product demand and volume is estimated to be 8 million devices per year, with a compound annual growth rate of 4%. We have identified two major target applications for our product. The primary application being medical, with an overall focus on wellness and comfort of living. And the second being botanical applications, such as people looking to increase the quality of indoor gardens. Both applications require an efficient humidifier that will best improve the quality of the air. We have included an exploded view of our product. It is important to note that all the electronic components are considered as one part. The fast diagram shown shows the main function, which is to humidify air, and the sub-functions the humidifier must perform.
So we have come with two potential assembly sequences, and we're going to be showing you them using the fishbone diagram along with the parts as they form the assembly with the images on the right. So first we're going to start with the tank cap for the first variation, followed by the water level sensor components, including the contact sensor shield and the sensor rod with the wick filter. This is followed by the silicone ring and the mid-body base ring. We then add the electronic components, followed by the two diffuser components, which include the LED diffuser and the diffuser top. This is then followed by the three housing components, which is the mid-body housing, the tank housing, and finally the cap. For the second variation, we start with the mid-body housing, which is then followed by the mid-body base ring and the silicone ring. We then add the electronic components, followed by the LED diffuser and the diffuser cap. This is then followed by the top cap, to which we add a subassembly of the tank cap, followed by the water level sensor components, which include the wick filter, sensor shield, and the sensor rod. And finally, we complete this with the tank housing. When comparing these two assembly sequences, we see that variant 2 seems to be the more likely sequence to go with due to the ease of testing subassemblies and the ease of assembling in parallel due to the addition of the tank cap assembly with the water level sensor components. We then created a function component mapping matrix, which matches the components of the product along with the functions from the fast diagram. In this, we see that prevent burns seems to be the most common, as it contains close to 5 components from the product. This could be a potential for inefficiency and could see a possible redesign.
This is our bill of materials along with the cost estimation. We use custompartnet.com to estimate the cost of material, processing, and tooling. We assume that the assembly was done manually and used an hourly rate of $20 per hour for an assembly line worker. Most of the manufacturing process is injection molding, but we can also see processes such as CNC machining and die casting. We also did purchase some of the components. The total cost ended up being $45.53. We classified the components of our product by importance of functionality and cost. As can be seen, no component was low in cost and low in functionality, or high in cost and low in functionality. Following this analysis, we found that we should redesign the sensor rod, LED diffuser, contact sensor shield, and the tank cap, as well as the electronics. We are excluding the electronics, sensor rod, and contact sensor shield, as these parts would be pre-purchased. Additionally, we want to reduce the number of parts from the assembly, and we will be doing this by redesigning the tank housing and the mid-body housing to create one part instead of two separate parts.
Functional differentiation table, you'll see that the only function different to customer groups is the control steam output function, which relates closely to our component commonality table where we obtain the tank cap as a module. This means that the tank cap needs to be redesigned to DFA. These are the two variations of the tank cap we came up with. The only major difference between the two of them is the size of the hole on the top. The relatively smaller hole is more suited towards medical customers, while the larger hole is more appropriate for gardening uses. Now, in our original product family assembly sequence, it starts with a tank cap which leads to two parallel lines, and this is not at all ideal for a product family assembly sequence. That's why we modified the sequence to have the tank cap come much later and started with the mid-body housing. This allowed this modified product family assembly sequence to have much more of the mushroom shape, which is much more preferred and much more ideal from a product family assembly.